Okay. All right. Well, good morning and happy Wednesday, week 9 Wednesday. Just a few more lectures left in the quarter. So anyway, today we're going to look at bootstrap-based hypothesis tests. So Monday we did randomization tests, and we said you can shuffle up your things and randomize, do a randomization test. Today we're going to do bootstrap-based ones, okay? Now, everything, both randomization tests and bootstrap tests and everything kind of, and your parametric tests like the t-test and stuff, they all rely on a sampling distribution. So in order for us to do statistical inference, we need a sampling distribution. The sampling distribution of a statistic is the distribution of all possible values of that sample statistic from all possible random samples, I guess of a given size, drawn from the population. And kind of the key uses are that by looking at this sampling distribution, we get a sense of how much a sample statistic can vary. And if we have data, we can compare the statistic from our observed sample with the sampling distribution under the null hypothesis, and we can decide, is my observed statistic, is that considered to be a rare and extreme event if the null hypothesis were true, or is it kind of like an ordinary amount of variation if the null hypothesis were true, or whatever, right? We can compare our observed thing to what the sampling distribution would be if the null hypothesis were true, and then make a decision on whether my observed sample is coming from that null distribution or if it's coming from something else, right? So we find the probability that the random sampling process could produce our observed sample statistic or something more extreme. That's our p-value, and we make decisions based on that p-value. A key thing that we use in kind of all of our intro stats classes is the central limit theorem. The central limit theorem says that the sampling distribution of your sample mean is going to follow a normal distribution as long as your sample is randomly drawn and your sample size is, quote, large enough. And we say, our x bar comes from a normal distribution where the mean is mu, the population mean. Standard deviation is sigma over the square root of n. And, that applies for the sampling distribution of the mean. But sampling distributions exist for really any statistic that can be calculated from a sample. Okay, so not just the mean, although that's kind of the one we most commonly use, especially in the intro classes, but sampling distributions exist for any other statistic that we can think of, such as the standard deviation, variance, or whatever. Those things might not follow the central limit theorem, might not follow normal distribution, but a sampling distribution does exist. It's just the idea of what kind of values can you get for this statistic if we have random samples drawn from the population. So for statistics other than the mean, we may not need to rely on our mathematical knowledge of probability distributions. It's good. It's good, and this is not to say just ignore the 100 series, okay? That is important. Your mathematical knowledge is an important foundation. But even if you don't remember everything, okay, it's okay, all right? We can use simulations to approximate our sampling distribution. Now, anytime you do a simulation, and really anytime you do statistical inference, and at the end of the day, anytime you do statistics, you have to make assumptions, okay? That's basically at the heart of statistics, is you have certain data, and based on this data, you're trying to fill in the gaps of your knowledge. And how you fill in those gaps in terms of the data you don't have is you're making assumptions, okay? So you have to make assumptions about the population, and so if you do a traditional t-test, you're assuming the central limit theorem applies in this case, okay? If you're doing one of these kind of simulated things, either you have to make assumptions about the population's shape or distribution, okay? Maybe assumptions about the mean of the population or standard deviation of the population or any other kind of parameters that define the population. Maybe you're just making assumptions of what kind of values could appear in the population, okay? But you are making some kind of assumptions. All right, and I know that always makes people a little bit uncomfortable, but there's no avoiding it, okay? And people come to different conclusions. You know, you can have two sincere statisticians doing their best, both coming to slightly different conclusions or completely different conclusions because they are making different kinds of assumptions, okay? And you know, who's correct is, you know, it's really going to come down to which assumptions were closer to reality. But anyway, once you've established your assumptions about the population, you can simulate the sampling distribution just by repeatedly drawing samples of a certain size from that population you know assumed or hypothesized about, and then recording sample statistics for each sample. Okay, so we're going to start off with the parametric bootstrap. Okay, so the procedure of simulating the sampling distribution by making parametric assumptions about the population, we call that parametric bootstrap. Okay, so we're going to make parametric assumptions about the population. Now, this general term of bootstrap comes from the phrase, you know, pull yourself up by your bootstraps. Okay, and that's the idea of like getting yourself out of a situation, you know, on your own, not relying on somebody to help you out or whatever, right? It's kind of like pull yourself up by your bootstraps. You gotta, I don't know, get yourself, you know, whatever. Where did this phrase come from? I don't know. There's all kinds of different theories. My personal favorite theory as far as the origins of this phrase, okay, you look up the etymology of this thing, it's like, who knows where it came from. But the one I like the most is there was a story of a folk hero who was walking around. One day he gets stuck in a swamp. He can't get out. But what does he do? He bends over, grabs his bootstraps, pulls himself out of the swamp. Okay? Of course, a silly thing, but you know, it's just kind of funny. All right. But anyway, we call these methods bootstrap methods because we are not going to try to gather more data. We just have the data that we have, and without external help, without trying to get more data, without trying to do other stuff, we're going to try to answer questions about the population just based on the sample I have. And so the way we're going to do that is we make assumptions, okay? And with parametric bootstrap, we're going to make parametric assumptions about the population. We're going to assume the population follows some specified parametric distribution, okay? Maybe we say the population follows a normal distribution, or the population follows a uniform distribution, or the population follows this distribution. We make assumptions about that. Okay. Once we assume the population, we simulate drawing a bunch of random samples from that assumed population, and then what we do is we calculate our sample statistic for each random sample. We do this a bunch of times. We record that sample statistic every single time, and then that's going to form our sampling distribution, our simulated sampling distribution. Okay, so let's say we have, okay, so there's the SAT, right? Did you guys take the SAT? Is that still a thing? It's kind of like optional now. Is it still recommended? I don't know. I'm like, no. It's not optional? It's required for some, I don't know. But for UCLA, it's not even considered? I don't even know. Well, anyway, the SAT, it exists, okay? And it's supposed to follow a normal distribution. The mean is 500, standard deviation of 100 for the general population of high school seniors, okay? The scores have a maximum of 800, so you can't get higher than 800. You can't get it lower than a minimum of 200. Scores come in increments of 10. So 640 is a valid score, 638 is not, okay? And in reality, scores are not normally distributed because only high school seniors who intend to go to college will take the exam, but we're not going to worry about that. We'll just assume scores are, in fact, normally distributed with a mean of 500, standard deviation 100. Let's say we take a random sample of 15 students, and then we want to ask questions about the variance. So we're going to say, what is the sampling distribution of the sample variance? Okay, do you guys remember the answer to this question? If you have a random sample drawn from a normal distribution and you look at the variance, the sample variance, what is the sampling distribution of the sample variance? Do we remember? We learned about this, right? In Stats 100B. Maybe are you taking that class now, or you took it last year? And we don't remember? Sampling distribution of the sample variance? Yeah. Chi-squared! All right. Professor Christo is relieved. Okay. But let's say you don't remember that, okay? We can just do this, all right? And technically, our thing isn't 100% normal because we have to do a couple things to it, because it's, SAT scores. So we're going to simulate drawing a random sample from our population. So I'm going to use our norm to get random normal values. I'm going to say I want 15 values. The mean is 500, standard deviation is 100. I use 15 normal values. I'm going to round it off to the nearest 10 place, okay? So you normally use round and you say how many places after the decimal you want to keep. You can actually put in negative values, and you can put in -1 and it will round to the nearest 10, okay? And then we're going to say if the value comes in greater than 800, just max it out at 800, okay? And if the value comes in less than 200, make the floor 200, and that's going to be our sample. So here's just 15 random values. I could say, hey, what is the variance of this sample of 15 values? And I get something a little over 10,000, okay? And that is my sample variance. Now, what I want to do is I want to do this a bunch of times. I'm going to say, all right, let's repeat ourselves 10,000 times. And so I just copied and pasted the exact same code, except at the end, when I calculate the variance, I'm going to store it in my vector. Sample variance is square bracket I. And I'm going to get 10,000 different sample variances. And now I can say, hey, what is my summary of these things? And sometimes my sample variance was as small as 1,540. Sometimes it was as high as 29,838. The average, the mean, is just over 10,000, just over 100 squared, okay? First and third quartiles are there and there. Here's a histogram of my sample variances. And yeah, that looks kind of like a chi-squared distribution. The answer to, the pop quiz, what is the probability distribution that we use? It's the chi-squared distribution. You might not have remembered, like with the chi-squared distribution, you have to know how many degrees of freedom to use. And so this would be chi-squared distribution with 14 degrees of freedom. And you have to use a scaling factor. And so anyway, we can apply that scaling factor, and I can compare my histogram of values that I sampled, shown in the histogram here, versus the theoretic chi-square distribution shown with the red line, and we see there's pretty close alignment, okay? Perfect alignment is if the red line goes right through the middle of each of these gray bars, and we're getting pretty close, not perfectly so, but pretty good alignment between the histogram, my kind of empirical sampling distribution, versus the theoretic one, okay? So yeah, the theory holds true, and when I simulated it myself, it looks like there's good agreement there. So if you didn't remember about the chi-square distribution for the sampling variance, that's okay. This is why we use Bootstrap, okay? Is that we just get around this by just simulating the sampling distribution, okay? And so again, let's say we have a sample of 15 SAT scores, and the variance of my sample of 15 is 20,000. And then I'm going to ask the question, is it reasonable to believe that this sample of 15 values was not randomly drawn from the population where the mean is 500 and standard deviation is 100? In particular, I want to know, like, is my sample coming from a population where the mean is greater than 100? Because I'm getting a variance of 20,000, okay? Where wait, what did I say? Is where my standard deviation is greater than 100? Is my sample coming from a population where the standard deviation is greater than 100? So again, we can ask, well, if the population actually does have a standard deviation of 100, what kind of sample variances can I get? Okay, most of the time I get variances around 10,000. Can I get a variance of 20,000? Yeah, it does happen, but not very often. It's kind of an extreme value, okay? Compared to every other kind of sample, like these are different samples of size 15 drawn from the same population where the standard deviation is 100. Sometimes we get a variance of 20,000 or higher, but it's kind of a rare occurrence, okay? And we can ask, okay, of the 10,000 sample variances, how many were greater than or equal to 20,000? I get a vector of true falses, I take the mean of that. So that happened 1.2% of the time. So out of 10,000, it happened 120 times. So if I have a sample where I have 15 values and the standard deviation or the variance is 20,000, I can either say, well, yeah, maybe my sample was one of the very rare 1.2% where this kind of thing happens by random coincidence. Okay, that is possible. Okay, but probably the easier explanation is to say, I don't think I was the lucky 1.2%. Rather, my sample is probably coming from a different population. Okay, coming from a population where the standard deviation isn't 100, coming from a population where the standard deviation is something a little bit higher. That's how I'm getting a variance of 20,000. Okay, is it possible that it came from the original population where the standard deviation is 100? It is possible. How often does something like this happen? It only happens 1.2% of the time, right? So that's a small p-value. You'd probably end up rejecting the null hypothesis, and you'd say, yeah, you know, the reason why I'm getting this kind of big variance is because I'm drawing it from a different population. Okay, so I would say, yeah, the empirical p-value is low enough for me to reject the null hypothesis. I conclude my sample of scores isn't a random sample drawn from the population where the standard deviation is 100. Okay. So that's for the sample variance. We could do the same kind of thing, but for different sample statistics. Okay, have I given you any answers yet? No, okay, let me give you your first one. First one is A. A as in apple. A as in apple is your first UQuiz answer. All right, so in this one, let's keep working with SAT verbal scores. And let's pretend we have a classroom of 25 random students, okay? And now, I don't know if classrooms are ever random, but let's just assume we have 25 random students. And what we're gonna do is we're gonna look at the highest SAT score. We're gonna say all 25 of these students took the SAT. We're gonna say who got the highest score, okay? And we're gonna say what's the probability that the highest score is 750 or higher? Okay, so that I think most people would say that's a pretty good score. Okay, 2.5 standard deviations above the mean. What's the sampling distribution of the highest score in the class, and what's the probability that the highest score in the classroom of 25 students, is going to be 750 or higher? Okay, now there is a theoretic distribution that you probably haven't learned that can be used to describe extreme values like the maximum value in a sample. It's the Gumbel distribution. But probably you're not familiar enough to really do a theoretic test with it. So we will just use parametric bootstrap as kind of a workaround to say like, okay, I don't really know the math, but we'll do parametric bootstrap, okay? Our assumption here is that we're assuming that the population follows a normal distribution with mean 500, standard deviation 100. It follows kind of the SAT rules. So this is what I'm going to do. I'm going to create a sampling distribution, 10,000 values. I'm going to do 10,000 random samples of 25. I say our norm, 25. I want 25 students to represent my classroom of 25. Okay. I round them off to the nearest 10. I set the max to 800, the min to 200. And then from my sample, I say, what is my maximum value? Okay. What is the maximum value? And I'm going to record that as my highest score. And I do this 10,000 times. So I'm going to get basically 10,000 simulated classrooms of 25 students And for each one, I'm going to say, hey, who got the highest score? What's the highest score? And no surprise, the highest values sometimes I get was 800, okay? The median, as far as the highest score goes, is around 690, and the minimum is 540. Okay, and this is the distribution that it looks like, okay? So actually it's not, the Gumbel distribution doesn't work because Gumbel doesn't actually have this hard cap at 800. It's like if you drew values from, normal distribution and you're just looking at the highest values, what's that? That would be that distribution. But here we've got a hard cap. But anyway, this is our thing, and we just want to know, okay, how often do we get a classroom of 25 where the highest score is 750 or higher? Okay, so we can ask that. What is the probability that the highest score is 750 or higher? We'll get around 16%. Okay, so if you take random samples of 25 students, there's about a 16.4% probability that the highest score in your class is going to be 750 or higher. Okay. All right. What if we had 50 students instead? What if we kind of joined classrooms or whatever, and we had 50 students, and we said, hey, who got the highest score in 50 among 50 students, and is that highest score 750 or higher? Okay. So just kind of intuitively, we would think, okay, well, the probability should go up, but how much up? Right? Well, we don't have to do any math. All we do is we just copy and paste the code that we had before, except instead of random samples of size 25, I'm taking random samples of size 50. Okay, do the exact same thing. All right, and so now my probability goes up to 29.2965, so just under 30%. So if you have random samples of 50 students, and you say, all right, who got the highest score here? What's the highest score in this classroom of 50? Now the probability that the high score is 750 or higher is closer to 30%. Okay. All right, and just kind of going along with this, like we could do even kind of more complicated things that I don't even know what distribution I would use. Okay, I don't know what the theoretic thing is here. All right, so let's say you have this kind of, I don't know, smallish, medium-sized high school. There's 200 students in the senior graduating class. Okay. And then the school administration is very proud of itself because 10 of its students scored 700 or higher on the SAT verbal. So this is a little bit cynical, but maybe the administration is like, oh, this is great. We're doing such a great job of preparing our students for college because look, we have only 200 students, graduating, but look at this, 10 of them got scores of 700 or higher on the SAT verbal. So is this something that the school administration should be proud of, right? Does this data that we have, does this sample provide evidence that the student body is something other than just a random sample drawn from the general population with a mean of 500 and standard deviation of 100? Like, if we just drew random samples, like, do we sometimes just get 200 students where the 10 highest scores are 700 or higher? Could that happen? All right. I don't know what kind of theoretic distribution to use here. But that's okay. We're going to just bootstrap our way through it, okay? So what I do is I say, all right, now I'm going to draw a random sample of 200 values from the normal distribution. This is going to simulate my 200 graduating seniors who all took the SAT. And again, I round them off to the nearest 10, set the max to 800, the lowest to 200. And then the key statistic I'm going to look at is I'm going to sort them from greatest to least, and then I'm going to take the 10th highest score. And I just want to know, is that score 700 or higher? So if it's 700 or higher, then all 10 and higher, have scores of 700 or higher, and if not, then no. So we're going to just sort them in decreasing order. We're going to record the 10th highest value, and we want to know how often is that 10th highest value 700 or higher. Okay, so I do this, and 10,000 times, and out of 10,000 simulated graduating classes of 200 students, 3.5% of them had, their 10th highest score of being 700 or higher. Okay, so my empirical p-value is 3.5%. So what that says is that if 200 scores were randomly drawn from the normal population, if this is just a random sample, then it's pretty unlikely for your top 10 students to all have scores of 700 or higher, okay? It could happen. It could happen by random chance, but it only happens around 3.5% of the time. So it's probably reasonable to conclude that the sample of students we have is not randomly drawn from the same population as everyone else, where the mean is 500 and standard deviation is 100, but probably is from a different population, okay? Now, whether the school administration can take credit for this result is an entirely different question, but we'd probably say, yeah, this does seem quite a bit different from just your ordinary random sample of 200 students. Okay, so this is kind of what you can do with Bootstrap, is you can start answering these kinds of questions where the theoretic distribution is kind of tough to do, right? So if you're comfortable making parametric assumptions about the population, then you can use parametric Bootstrap to simulate the sampling distribution. And then once you have your sampling distribution, then you can do hypothesis tests, find p-values, do statistical inference, okay? Parametric Bootstrap has higher power as long as your assumed distribution is correct, okay? The great flaw in parametric Bootstrap is if your assumptions are wrong, then everything is wrong, okay? We have non-parametric Bootstrap, all right, which I'm going to introduce next, and that makes fewer assumptions or different kinds of assumptions, okay? No parametric assumptions about the population, different assumptions. It's going to be less efficient, though, all right, than if you did know the parametric distribution, right? So making parametric assumptions are basically stronger assumptions, but maybe could be wrong, okay? All right, let me give you your second U-quiz answer, and that is C as in cat. C as in cat for our second U-quiz answer. All right, non-parametric Bootstrap, So this is probably, when somebody talks about Bootstrap, they're probably talking about non-parametric Bootstrap. This is kind of the default term that Bootstrap refers to, okay? And as the name would imply, non-parametric Bootstrap does not make any parametric assumptions about the population, okay? The assumption, you do have to make assumptions, and it's a different assumption. The assumption in non-parametric Bootstrap is that our sample was drawn randomly from the population. Okay, so if it's reasonable to assume that your sample is drawn randomly from the population, you can do non-parametric Bootstrap. Okay, and then the next part is, okay, if our sample is randomly drawn, it is reasonable to believe it is representative of the population. Okay, so probably everyone's okay with that. All right, if we got a random sample, it's reasonable to think that my random sample is representative of the population. Okay, now the next part, which feels a little bit more heroic, but this is really the natural conclusion of where things go. If you assume your sample is representative of the population, then what we can do is say, all right, well, I don't have the actual population, but my sample is representative of the population, so I'm going to use it as a stand-in for the population itself. I'm basically going to just take my sample. What if I just cloned it a whole bunch of times? I duplicate my sample like 1,000,000 times. And now I've got this big entity, and you can call that thing the population, all right? And that's basically what non-parametric Bootstrap does, right? I don't know if you've ever played with like Photoshop or something, but like, let's say you needed to fill in part of the picture with like a bunch of grass. What you can do is like, you can like take a little patch of grass and then like clone it everywhere, right? And you just kind of copy and paste that grass everywhere. And then now it looks like the whole picture is filled in with grass. And if your patch of grass is like representative of your average patch of grass, then it will probably look okay. Now, if your patch of grass has something weird in it, and then you clone that everywhere, then your field is going to look funny because you're going to have that weird thing show up everywhere multiple times. So the same kind of problems happen. If your random sample has some weird outlier in there, then when you duplicate it or clone that a bunch of times to fill in your population, it's going to look a little bit funny. Okay, but the hope is your random sample is representative, and then so therefore when you kind of clone it a whole bunch of times, you have something that reasonably looks like the population. Okay, now you don't actually have to duplicate your sample a bunch of times. Mathematically, you can just resample with replacement. You just draw from your sample with replacement, and that is mathematically equivalent to making infinite copies of your sample. Okay, and so that's what we do. For a non-parametric bootstrap, we just take our sample and we will resample it with replacement, and that's going to stand in for our population. Okay, so just to kind of compare bootstrap resampling versus, say, the randomization test, which we saw Monday. Okay, and I guess parametric and non-parametric bootstrap. So if the data you have was obtained via random sampling, you can do non-parametric bootstrap. Okay. If the data you have was obtained via random sampling and you are willing to make parametric assumptions about the distribution, then you can use parametric bootstrap, right? If the data was not obtained via random sampling, but you have random assignment with an experiment, then you use a randomization test. Okay, so that's kind of the key difference. Random sampling, non-parametric bootstrap or parametric bootstrap. Random assignment, randomization test. Okay, at a practical level, it's just one difference in your line of code. Okay, in R, when you call sample, for randomization test, you do replace equals false, or you just leave it off. Okay, because the default value is replace as false. In Bootstrap, you have replace equals true. Okay, replace equals true, resamples with replacement. And that's kind of like the practical level. Now, the implications theoretically are quite a bit different though, okay? But when you sample with replacement, that would work if you have a random sample, okay? But in both of these cases, what we're trying to do is we're trying to simulate the sampling distribution and say the source of variation is basically the random process. Okay, in randomization test, it's the random assignment of treatments. In Bootstrap, it's the random sampling process. Okay. All right. So I'm going to use this example coming from our textbook. Okay. This is like an old study based on the 2000 census, and the study itself was done in 2006. They're doing. It was run by the Center for Immigration Studies at the U.S. Census Bureau, okay? And they were looking at the immigrant population coming from Latin America and also Mexico specifically, all right? And so they looked at a bunch of immigrants, and they were tracking educational achievement, okay? They wanted to see is there a difference between immigrants who come from Mexico versus all other Latin American countries in educational achievement. Educational achievement or attainment would be like, did they graduate high school? Did they graduate college? Did they get a higher degree? Things like that, okay? So there are the issues with the study is, they have in their data, they looked at 150 immigrants in Los Angeles coming from Latin American countries. And as far as the population goes, they kind of separated out immigrants coming from Mexico, and then they grouped all other kind of Latin American countries together. Now that's questionable whether that's a good, reasonable thing to do, considering there's a great diversity in terms of the other Latin American countries, but also from kind of a practical standpoint, because there were only kind of 150 people in total, and if you look at the data, 116 came from Mexico, and then when you grouped everybody else together, you only had 34. Okay, so it kind of, from a practical standpoint, it's difficult. If you wanted to kind of split up all of the different countries, you might only have like one person from, say, Ecuador or something like that. Okay, and if you only have one individual, you can't really do any kind of study because you have 0 degrees of freedom with one individual. So, and even if you just have 2, that's also really kind of troubling. So I think from a practical standpoint, they just said it's going to be Mexico versus all other Latin American countries. Again, there's issues with that, but just with the data they had, this is the choice that they made. These are the different variables that were included. Again, older data set. So if you look at like the immigrant year, which will be the year in which the immigrant arrived in the United States, would be something around, you have like a lot of people coming in like 1960, 1970, and things like that. Okay. The measure of educational achievement is a number between 1 and 100. Now, unfortunately, I have no idea what these numbers mean. Like, if somebody has education achievement 100, what does that mean? Does that mean they got a PhD? Does that mean they got a medical degree? Does that mean they got multiple PhDs? I have no idea. Okay. If somebody graduates high school, what number is that? I have no idea. Is that a 40? Is that a 50? A 60? I don't know. If they went to college, or if they graduated with a bachelor's degree or a master's degree, I don't know what numbers those correspond to. So that's kind of a big drawback, or kind of contentious point I have with this data. But it just says 1 is lower and 100 is higher. Okay. And then the other kind of variable of interest to us is, did this individual come from Mexico? Okay. And we're going to have 1 for people who came from Mexico, and 0 for people who came from any kind of Latin American country. And so this is just kind of the data we see. And so, we can see, this person came in 1959 and their education achievement score is 39. Again, no idea what that is. Okay. This person has a 46.2 and this one has a 46.8. So I don't even know what that means. Does that mean like this person went to like school for 2 more days than the other person? I don't know, but it's a little bit strange that we have these things. I don't really know. Okay. But anyway, different people, and then, different kind of values. But here we're going to look at, we're going to split on this variable for Mexico versus, so we have 116 people who came from Mexico, 34 who came from other Latin American countries. When you take the mean of the education achievement score, the mean for people from other countries was 64.5. The mean for people from Mexico was 58.6. So the difference between these two values, the difference between observed means, is negative 5.9. And the question is this number statistically significant? Okay, is this difference statistically significant? Negative 5.9. Here's just kind of a box plot. So we have, more spread, but probably a result of just having more observations, 116 versus 34. The median is a little bit different. The question is, is the difference in means, is that significant or not? Okay. Density plot. We got, the red versus the blue or the teal and salmon. I don't know what colors these are. What is the name of this color? I don't know. Okay. Anyway, is there a difference here? I don't know. Okay. The traditional analysis, we'd probably do a t-test. Okay. We would do a t-test to compare the means of 2 independent samples. And your null hypothesis would be that the mean for immigrants coming from Mexico versus the mean for immigrants from other Latin American countries, that there's no difference between them, that the difference between them is 0. And the alternative is that there is a difference. We could the assumptions to use the t-test is probably okay, because we've got big enough samples of 116 and 34, probably big enough to use the apply the normal distribution. And so, this p-value is probably pretty accurate, and we get a p-value of 0.0459. Okay, just under 5%. And so this would say, yeah, you know what? the difference between 64.5 and 58.59 is just big enough to say it is statistically significant, not the result of just kind of randomness. Okay, your confidence interval goes from 0.1 to 11.7. So, on the lower end, it is just above 0.1, just above it. But again, that is technically enough for us to say it is statistically significant. Okay. What we'll do now is we'll do non-parametric bootstrap. Okay. So again, with non-parametric bootstrap, we're going to resample our original data with replacement, okay, because we're assuming our sample is representative of the population, okay. We're going to try to create our null distribution, our null sampling distribution, or our sampling distribution under the assumption that the null hypothesis is true, okay. Remember, the null hypothesis says that the mean for both groups are equal. Okay, so effectively, that would say that the values that we're getting, if the null hypothesis were true, is saying that the values for education achievement for immigrants from Mexico are coming from the same population as education achievement scores for other Latin American countries. Okay, because if the null hypothesis were true, we're saying that the means are the same, so therefore the values we're getting are coming from the same population. So what we're going to do to simulate our samples is we're going to just pool all 150 values together. I don't separate the 116 values from Mexico and the 34 values from other Latin American countries. I don't keep them separate. I just pool them all together into one population of 150, or one group of 150, because that's what we would have if the null hypothesis were true, and that's what we're trying to simulate. We're trying to simulate what could we get if the null hypothesis were true. So we put all 150 together, then I'm going to draw 116 values at random with replacement from the 150. Then I draw another 34 values with replacement from the same group of 150, because that's what we're saying if the null hypothesis were true, okay? A common mistake students make is that they keep the 116 separate from the 34, okay? Don't want to do that, because that is what you would have if the null hypothesis were not true. You have your 116 different from your 34. But what we want to say is, what kind of values can you get if the null hypothesis were true? And in that case, all the values are coming from the same, okay? So we're going to sample the same set of 150 values with replacement, and we're just going to see, hey, what kind of values can we get that are different? We're going to repeat this a bunch of times. So this is what my thing looks like, okay? Latino $achieve, this is the vector of 150 values. All of the scores are just pulled together in this one column. I'm going to draw 116 values with replacement. I'm going to call that group A. I draw 34 values with replacement. I call that group B, and I just say, hey, what is the mean of group A and what is the mean of group B? Okay. Sometimes group A has a mean that's higher than group B. Sometimes group B has a mean that's higher than group A. Sometimes the mean is bigger than 5.9. Sometimes it's less than 5.9. Okay. We want to see what kind of differences we can get. Okay. And so we do this. And again, my observed difference was negative 5.9, and I want to see how often do we get things that are more extreme than my observed difference. Now, because it was negative, and if I did absolute value, that's not going to work, okay? So you have to put absolute value on your observed difference, so we're going to say, all right, and absolute value on our vector of differences. And we say, how often do we get a difference of 5.9 or something more extreme? And when we do this, this happens around 4.6% of the time. So we get an empirical p-value of around 4.6%. Okay, this aligns with what the t-test did. Okay, our t-test, when we ran it, we got a p-value of around 4.6%, 0.04597. Here, when I run Bootstrap, I get something right around there, 0.0465. Okay, and again, less than 5%. So if my significance level is 5%, I would reject the null hypothesis. So that would be how we do non-parametric bootstrap, okay? We could also do parametric bootstrap. Here, wait, before I forget, one more? Okay, last view quiz answer is E. Last view quiz answer is E. Okay, so parametric bootstrap, we're going to make parametric assumptions. So non-parametric, we just resampled the data we had. Parametric, we're going to make parametric assumptions. So here we're going to assume our values come from the normal distribution or something like that, okay? But again, if the null hypothesis were true, we're going to say both of our samples are coming from the same population. We're trying to simulate our sampling distribution if the null hypothesis were true. So, how often do two randomly drawn samples have a difference of 5.9 or greater if both samples are drawn from the same population? So we are going to use R's, R norm function. So here I'm going to calculate the overall mean of the 150 values. So I do Latino $ achieve, calculate the overall mean, that's going to be M, calculate the overall standard deviation of the 150 values, and I'm going to plug those into our norm. So group A is going to be 116 values drawn from the random normal, where the mean is M and the standard deviation is S. Group B is going to be 34 values drawn from the random normal, where the mean is M and the standard deviation is S. I'm using the same values here, again, because if the null hypothesis were true, we're saying both groups are coming from the same population, okay? Again, common mistake students make is they keep the 116 separate from the 34 and they have a different mean for the 116. They say, all right, what's the mean of my 116 immigrants who came from Mexico? And they use that for this. And then what's the mean for the, the 34 immigrants from other Latin American countries, and they use a separate mean for that. Okay, you don't want to use different means there, because we want to say if the null hypothesis were true, they're effectively coming from the same population, and you want to compare your thing versus what distribution you get if the null hypothesis were true. Okay, so we use the same M, same S for both groups. We say, well, how often are my group means different of 5.9 or more? We get an estimated p-value of around 4.6% again. So all of these things are kind of aligning, and they all kind of they seem to agree with each other. So that's a good sign. Okay. With parametric things, you kind of want to make sure your distributional assumptions are reasonable. So here our distributional assumption was that the population is normal, and we look at this and we go, I don't know. I don't know if it's reasonable to say this looks like the normal. So maybe it's a little bit risky. You can do a QQ plot and you go, oh yeah, this is a little troublesome, but maybe it's okay. I don't know. All right, we had big enough samples, 116 and 34, so maybe we'll get away with it, okay? And so, yeah, at the end of the day, what we're trying to do is we're trying to figure out what kind of value we can get of our sample statistic for the different samples drawn from the population. That's going to help us figure out our p-values and do other kind of statistical inference. And then, as far as parametric bootstrap, we're assuming our data comes from some known parametric family, okay? Maybe the normal, maybe some other kind of thing. But could be wrong if you have the wrong assumptions there. And then non-parametric, we just use our existing sample as a stand-in for the entire population. Okay, so that is your lecture on bootstrap hypothesis tests. We'll wrap things up here. Have a great rest of your day, and we'll see you Friday.